Hello everyone. Here I am going to present my paper Genetic Algorithm with Modified Reproduction Operators for Grammatical Inference. I will begin with abstract, which is given here. So what I want to do, I want to develop a algorithm for grammatical inference where I am going to use genetic algorithm, and in order to validate production rules, I have implemented push-down automata simulators, and in order to address the issue related to regularization and generalization, I utilized minimum description length principle. So what is grammatical inference? Grammatical inference is a methodology to infer context-free grammars where we provide input of text in the form of positive and negative sentences or strings, and the learning algorithms produces context-free grammars. So all in all, what we want to do, we want to produce a context-free grammar from set of data. The proposed methodology is given here, where you can see our methodology is divided in two phases. In phase one is basically construction of grammar and verification of production rule. On the other hand, in phase two, I'm implementing our genetic algorithm for grammatical inference, and at the end of both the phases we will get context-free grammar with fitness function value. And in order to implement this methodology, there are several phases we need to complete, which we need to complete for grammatical inference as well as for genetic algorithm. So the first step of genetic algorithm is generating initial chromosomes, which you can see here. So initialization and symbolic grammar representation. So we have created binary chromosomes, which you can see BC represents binary chromosomes, and we use the coding techniques for generating terminals and non-terminals. And then using this coding techniques, we created symbolic chromosomes, which you can see here. SC represents symbolic chromosomes. Then after creating symbolic chromosome and binary chromosomes, which we have converted in the form of symbolic chromosomes, we have evaluated the fitness function. So for the fitness function, this is our fitness function, where PS represents positive sentence, NR represents rejected negative sentence, NA represents accepted negative sentence, PR represents rejected positive sentence. So using this fitness function, we have evaluated the fitness of our chromosome. For reproduction operation, we used the Boolean based crossover of and mutation operation. So you can see here, initial parent populations are P1 and P2. A random mask has been generated, and then we have applied some Boolean based operators to produce subchild, and then we applied inverted mutation operation for mutation, where we applied XOR operators for creating the new child offsprings. For performing the experiments, computer simulations, we have created a robust experimental environment. As you know, genetic algorithm is population-based meta-heuristic algorithms, where some control parameters affects the overall results. So here I selected 5 control parameters. PS, you can see in this table, PS represents population size, chromosome size, production rule length, crossover rate, and mutation rate. And 2 levels are set for setting the robust experimental environment, which you can see here. Column 1 represents label 1 and column 2 represents label 2, and signal to noise ratio based approach is used, where I used the Tagachi signal to noise ratio with orthogonal matrix approach. And this chart shows the effect chart of all the factors involved during the robust experimental process. Through this experiment, you can see here the minimum smaller is better. So the smaller signal to noise ratio of each factors has been selected for conducting the experiments. So for first phase I implemented this algorithm, and for second phase I implemented this algorithm. This is for grammatical inference using genetic algorithms. So initially binary chromosomes have been generated, then mapping, creating symbolic chromosomes, then running the genetic algorithm, applying reproduction operation, determining the fitness function value, and repeating the process until the termination condition meets. If the termination condition meets, then we will stop and then we will display the final context-free grammar, fitness value, and elapsed time t. Experimental results reveals that our algorithm was capable of inferring the context-free grammar without getting stuck at local optimum. And we compared our algorithm with other algorithms like ITBL, BMOGA, bit mask oriented genetic algorithm, genetic algorithm with minimum description length principle. This is our algorithm, and GAWS algorithm. And this results reveals that our algorithm, that is the proposed algorithm, GIGA algorithm, showed a better result as compared to any other algorithm on all the 4 languages we used for our experiment. In order to derive a sound conclusion, fair conclusion, we conducted a statistical test. For a statistical test, hypotheses were defined, and the result of a statistical test reveals that null hypothesis got rejected because ANOVA test, here the p-value is lesser than 0.005 at 95% confidence interval. So we rejected null hypothesis. And in order to determine which algorithm is responsible for this rejection, we conducted a multiple comparison test. The result of multiple comparison test reveals that our algorithm showed either significantly better performance as compared to other 4 algorithms, or higher fitness value. It showed higher fitness values as compared to other 4 algorithm we implemented for on these 4 languages. The conclusion is presented here. The conclusion of our paper is presented here. So in this paper, we implemented a GIGA for grammatical inference. That is this algorithm. We implemented push-down automata simulator for production rule verification and its validation. Boolean based operator, reproduction operators were implemented for crossover and mutation operations. Results reveals that GIGA, our algorithm GIGA, grammatical inference using genetic algorithm, showed outstanding performance. It outperformed over other algorithms, or showed significantly better performance as compared to any other algorithms. In future, our plan is to implement GIGA for natural language and for domain specific language, which is presented here.